We're going to start with transformation of functions. We're going to start getting into, I'm not going to say it's a totally difficult, but it's a little bit difficult area to work with at first. But we do need to understand transformations to understand things like vertex form of quadratics. There's a few other things we're going to need it for. Just your common functions here. Just to go through them again, because these are ones mostly we're going to play with. We have your constant function, which is f(x) is just going to equal c, where c is just a number, a real number. So this would be like f(x) is equal to 5. You have absolute value, which is going to be f(x) is going to be equal to the absolute value of x. Your standard quadratic function is f(x) is equal to x squared. Your square root function, you see that, your cubic identity is f(x) is equal to x, and then your cube root, which is going to be the cube root of x. So these are what we call your parent functions. These are not necessarily all your parent functions, but the ones we're going to use now. We have some transcendental functions we haven't covered yet. But like I said, these are your parent functions. So this is the standard form of a quadratic. This is the parent function. But we'll make it a different function because we already used f(x). But if I take it, and let's say I add to it, well, now it's a different function. But we still have that parent component where we have the x squared. We have x minus 1 squared. X minus 1 minus 2x plus 1 is what it would spread out into. That is another example of a function that is based off that quadratic. So it's based off that parent function. We have the x squared component into it, but we're getting a different function. So parent functions are the most basic form of all your functions. So these are my most basic quadratic. And then what I do is I use my transformation to make new quadratic functions based off the parent. So if you understand how transformations work, it makes some things easier as far as graphing. So just some basics on these. So your basic constant function is going to look like this. It's just going to be a horizontal line. It's going to have a domain that consists of all real numbers, but the range is only going to be that value of c that the function is. This is like 1.5. So my range is just 1.5. The function is consistent, it's not increasing or decreasing, it's consistent across everything, and it would be considered an even function because if I flipped it over the y-axis, we get the same function back. This is your basic identity function. So whatever x is, that's what y is going to be. So if if x is 3, then y is 3. So you end up with a line like this. So this is really kind of your basic linear function. So this is your parent to non-horizontal linear functions. What we see here is my domain is going to be all real numbers. My range is also all real numbers because it's going forever on both ends. And in this case, it's going to be increasing for all real numbers. And this one's odd because I'd have to reflect it over x and then, reflect it over y, then reflect it over x. I need the two reflections and then we get the same graph back. Or you spin it 180 degrees and you get the same graph back. Like I said, so when we start adding on to these parent functions, start doing our transformations, some of these things like their domains and ranges where they're increasing, decreasing, that will change. So your basic absolute value function is going to look like this. It's going to be a V. So it's kind of like two identities here, one going down and one going up. The domain of this function is going to be all real numbers. The range, however, is going to be starting at 0, so we include 0 to positive infinity. It's decreasing from my x values from negative infinity to 0, but from 0 to infinity increasing, and this one is even. All right, I'm going to speed up a little bit. So we've seen quadratics before. Standard quadratic, like I said, the parent to all quadratics is going to be x squared. My domain is all real numbers. Once again, my range, because it's very similar to absolute value, is going to be starting at 0 to all real numbers. Sorry, from 0 to infinity, and then decreasing from negative infinity to 0. Remember, this part's just x values, and increasing from 0 to infinity. And this one's also even. Your square root. Your square root is going to look like this. We'll see more about square roots as we go along, but square roots really only exist as far as your basic square root of square root of x, only exists in the first quadrant. Its domain is 0 to infinity. We include that 0 because you could do the square root of 0. The square root of 0 is 0, so your range is also 0 to infinity. And this one is increasing across this entire domain, well, essentially from 0 to infinity. This one's neither even nor odd. It's mostly want to just know what these basic graphs look like, so when we graph these later. Your cubic, this is going to look like this is a basic cubic. So we'll see a lot more of cubics as go along. Here, once again, domain and range, all real numbers. This one increases across all real numbers, and it is an odd function. We're almost there. And then your cube root of 3, another one we might use. It looks kind of similar, right? We'll see why it looks like this. It has to do with reflection when we talk about inverses. As domain and range are all real numbers, increasing in all real numbers, also odd. So like I said, that's your basic parent functions, and that is what we're going to use for the most part when we're talking about all these kinds of transformations. So we're going to talk about what we call vertical shifts at first. We're going to let f be a function and c be any positive real number. We'll put this in Desmos in a minute so you can see this in real time. But the graph of y equals fx plus c is just the graph of y equals fx, but everything is going to be shifted up vertically by c units. So where this point, one would have a point at xy, this one now has a point at x, y plus c. So all those units shift up by c. However, if I do subtraction instead, fx minus c, that's just a graph of fx, but c is shifted down vertically c units. So if I had a point xy here on the transformation, x would stay the same, but now all my y values have shifted down or are decreasing by c. Okay, so like I said, we're going to do this in real time instead of using the slides. So what we have here is that x, which is equal to x squared, is going to give me this nice parabola. We've seen that before. So let me pick a point here. We could talk about it. There's a point here at 1, 1. So if x equals 1, fx is going to also equal 1. So we're going to see what happens to this point. So if I take fx and I add 2 to it, what we see is the entire graph shifts up 2 units. So we started here at 0. Now we moved up to here to 2. This point moves up to here and is now at 1. Sweet. So it's shifted up 2 units. So what we can also say that this is just representing x squared plus 2. So that is what we talk about as a transformation. The parent function is the x squared, and then we add this 2 to it to get a new function that is everything shifted up by 2 units. There we go. Just trying to get the next one here. So we have fx minus 2. We see we get the green one here. Now what we see here is that instead of being here at 0, 0, we shifted down to negative 2. This point that was at 1, 1 has now shifted down here and is now at 1, negative 1. So from here to here, y increased by 2, and from here to here, y decreased by 2. And also this is just fx is x squared. We can rewrite that as x squared minus 2. So that is a vertical transformation. If we add, we shift up. If we subtract, we shift down. So we always think about this as fx is just y. So the transformation is on y. So it's that y component that we see changing here. So horizontal shifts, so that means we want to shift horizontally along the x-axis. So this one's going to seem a little different, but we're going to let f be a function and c be a positive real number again. This time, we have c is directly on the x. It's not on the f of x, it's on the x. So it's inside the function. This is counterintuitive what you think it might be. Y equals f of c, x plus c is the graph of y equals fx, except everything is shifted left by c units. That's in a negative direction. It's shifting to the left. We have a point here, xy. What we get here is that we're going to get a point x minus c y. So the reason that happens is that these are going to be the same y values. So I have to replace x with x minus c to counteract that c. So that we're back to fx, and we know that fx should equal that y. So to kind of give us back that same value. So that's why it does the opposite. So anything that's directly on the x is going to do the opposite of what you think. Anything on the y pretty much does exactly what you think it will do. Like I said, this one just takes a little bit. It'll confuse you at first, but you'll get used to it. Y equals f of x minus c is the graph of y equals fx. But now everything shifts to the right c unit. So it's going to shift in a positive direction. So if we add directly to x, we move backwards. We move in a negative direction. If we subtract directly from c, we're going to move to the right, but we're going to move in a positive direction. Once again, same idea here. If I have a point here that is xy, then I'm going to have a point here that's going to be x plus c equals y. Showing you how the point transforms. And we need that because I would have to enter in x plus c into the transformed function. Once again, to get fx back so I can get the same y back. So it has to do with the fact that the y's are being stationary and the x's are moving. If you're not sure about this part down here, right here, you don't have to repeat this part. It's just sort of kind of give you an explanation, but mostly just remember, if I add directly to x, I'm going to move in a negative direction. If I subtract directly from x, I'm going to move in a positive direction. So going back to, oops, let me turn these ones off for a second. Go back to fx is equal to x squared plus 2. We're going to pick our favorite point again. Oops, I need my red. Pick my favorite point again at 1, 1. We know that is on x squared. So this time we're going to go directly inside of x, and we're going to subtract 3. So notice when I subtract 3, oops, got my tool moved to the other window. So when I do that, we see at, if we're centered here at 0, 0, now we're centered here at 3, 0. This point has moved over here to 1, 4. Do that backwards. 2, 4, 1. What we see here is that the x component is increased by 3. So we subtract 3, but we increased by 3 when we graph it. So if you were to go back and rewrite this without the function notation necessarily, so remember that your x is replaced now with x minus 3. So this is just x minus 3 squared. Or you can say this is x squared minus 6x plus 9. So we'll do this one more time, but now we're going to add 3. So when we add 3, let me turn that on. We see that we went backwards. So now our favorite point here, 1, 1, has now moved over here. It has moved to negative 2, 1. That means this x value has decreased by 3. Well, you can see here from moving from 0, 0 to negative 3, 0. So everything moved backwards 3 units. And once again, if I was to rewrite this without the notation, so f of x plus 3, well, we just replace my x here with an x plus 3. So that is really just x plus 3 squared, or like I said, if you want to expand that, that's just x squared plus 6x plus 9. Okay, so below is the graph of our f of x. We don't know what f of x is, that's not important, but this is f of x. So on the same axes, we want to graph the function f of x minus 3 plus 4. So we'll start with the easier part. We'll do the plus 4 first. The plus 4 means we're going to shift up 4 units. Right, because this is on the outside of my function. So this point right here would shift up 1, 2, 3, 4. This point here would shift up 1, 2, 3, 4, and this point shifts up 1, 2, 3, 4. So this is my f of x, but I just did the 4. So I'm going to label the other one in black so it makes it a little easier to look at. F of x. The red's going to be my final one here. So if I do this part here, I'm subtracting 3, so I'm going to shift in a positive direction, right? So I'm going to shift right 3 units. So now we go back to this part right here because I already shifted up. Now we just need to shift right 3 units. So this goes from here to 1, 2, 3. This point goes 1, 2, 3. And this point goes 1, 2, 3. This would be f of x minus 3 plus 4. Let's get my little friend out of the way here. So everything's shifted up 4 units and then shifted right 3. Now we have f of x is going to be, we have the same f of x, but now we're going to graph f of x plus 2 minus 1. So we could do this all at one time. We don't have to do it in groups either. So we know that we shift, according to this, we're going to shift down by 1. And then according to this part, we are going to shift because we're directly on the x and we're adding 2. That means we shift in the negative direction. So we're going to shift left 2. You pick bright red here. So this point here would shift down 1 point, and then it's going to shift left 2 points. So it's going to go here now. This point right here, shift down 1 over 2. This point right here, shift down 1 over 2. Let me get my little extra points out of the way. So we just need a couple points to get the basics of what the graph's going to look like. Try to graph these on here. It's not going to be perfect. I'm just doing the best I can here. Hard to draw smooth lines on this, but that is going to be our new function here, f of x plus 2 minus 1. Everything shifted down 1 unit, and then it shifted left 2 units. So take a moment and work on this worksheet problem. So here you have f of x. It's a completely new graph here. So remember, we have an open point and a closed point. So make sure that you do graph those. So just pick, I will tell you what point to pick here. I would move these points because these are important parts that give me the basic look of this graph. And those are the ones I would use to transform. So we want to transform this. So now we get our new function f of x plus 1 inside the parentheses and then minus 1 outside the parentheses. Okay, so we see here that we are going to, got a tool in my way. This little component here is going to cause us to shift. Remember, it's a plus on the x, so we're going to shift backwards. We're going to shift to left by 1. And this little part here is outside of the parentheses on outside directly on the y, so it's changing the y component. That's going to shift up or down. In this case, we're going to shift down by 1. So I didn't quite leave the room here for 1 point, but this point is going to shift left 1, down 1. So we get that point right here. This point here, where we have like a maximum, it's going to shift left 1, down 1. This point here, where it's minimum, we're just going to shift left 1, down 1. And then this point here, just pretend we know where this is going, is going to shift left 1, down 1. And that one, remember, needs to stay open. Let me get rid of my axis stuff here. So I got my new points where they're supposed to sit. So my graph now looks like this. Sorry, I'm having a hard time getting it smooth out there. Yeah, I think that's best it's going to do. But yes, that's my new function where everything is shifted over and down. Okay, I moved another point, so there's a more smoother version of what that graph should look like. Reflections. Oops, let me go back one. Reflections, this is going to kind of come back to like we were talking about symmetry over x and y. So some of this may seem a little familiar. Graph of y equals negative fx is the graph of y equals fx, but it's reflected over the x-axis. So what we're going to have here is that we reflect over the x-axis of a point xy here, and I reflect over here. The only thing that changes is, oops, that's y-axis, silly me. We reflect over the the x-axis. The x value will stay the same, but my y value will turn negative. So point here that is at x, y. Is going to turn into a point that is going to be at x negative y. So that is why that negative is right here, because it's the y component that changes from positive to negative. If I reflect over the y-axis, so at a point x, y here, and I reflect over the y-axis, then what we see here is that the y value stays the same, but now x would be negative, would be in the same spot. So the graph of y equals negative f of, or sorry, equal that y equals f of negative x. So the negative on the x now is the graph of y equals fx reflected about the y-axis. So instead, a point here that's xy now here becomes a point that is negative x, y. Oops. So just to show you what it's looking like here with something that's sitting still. Um, this is going to be fx equals the square root of x. So if I wanted to do this reflection, I want to figure out what fx is if it was equal to negative fx. Let's make that g of x. Then what we'd say here is that g of x is just your, but with a minus in front of it. Because we recognize that this part here is just f of x, which we have up here to kind of help you kind of go backwards if you need to do this. What we're seeing is just a reflection about the x-axis. So this point here that we have at 4, 2, all of a sudden is going to reflect down here. And now that point is going to be at 4, negative 2, because it's just the y component changes. We have a point here at 0, 0. But with that reflection, that point stays at 0, 0. So one of the things that happens when you're talking about reflections is that sometimes your things like your zeros, we'll see this in stretches too, but your zeros will stay in the same place. So here we have f of x is going to be the square root of x again, but this time we're going to have the graph over here of square root of negative x, which you might be going, well, I can't do that, but that's fine because all I have to do is put in negative x values. So then I'll have, like if I put in negative 4, then I have a negative negative 4, so I do square root of 4. So it's going to move it over here. So what we see here is that the negative is directly on the x, so g of x is just of x, but the negative is directly on the x. So once again, this point here that we have at 4, 2. Now all we're doing is we're just changing x from positive to negative, so it's going to flip over here, and it's to become negative 4, 2. And once again, we got a point here at 0, 0. So this y component, y times negative is, or sorry, 0 times negative stays 0. So you don't have positive or negative zeros, so that point stays there. All right, so going back to this graph again, this is my fx, but I want to have the graph of negative fx. So remember, this is just y, so I'm saying I want negative y. So what that means is that this point here, we have at negative 1, 1. Well, if we're going to change y's from positive to negative, it's going to flip over here and now become negative 1. Oops. So that negative 1, negative 1. Next, I'm putting that a little different. Just going to move over here. So we're going to have negative 1, but now that y becomes positive 1. So you're seeing that we're going to reflect over the y axis. Sorry, that was a complete brain melt down there. Let's try that one more time. The negative is here. Yes, the negative is on the y, but flipping the wrong points there. Negative 1, negative 1. The y component shifts up here. Sorry. I'm sure you're staring at me going, what in the world is she doing? No, it flips up here. So we're flipping it over the x-axis. When I wrote y-axis, I'm like, no, that's not right. Both reflect over x. If we just do this a couple other points, we have the point at 0, 0. So 0, 0, if I reflect it, it's at 0, 0 because we have y is going to turn into negative y. So 0 is going to turn to negative 0, which is 0. This point here is going to be negative 2, 0. And once again, The y component is 0. So a -0 is just going to stay 0. So pick another point to help us with this. So if you picked this point here, that point's at 1, 1, 2, 3. So the negative y is going to flip it down here to a point at 1, 2, 3, a point at +1, -3. So let me get rid of that point and this point. So what we have here is that we're going to do this. So the place you got to be careful with is sometimes those zeros. Just pay attention in this case that all it's changing is that my y's are changing from positive to negative or negative to positive, but my y's are changing sign. But that causes a reflect over the x-axis. All right, so on the same set of axes, we want to graph the function f of negative x. So the negative is directly on the x. So here, we'll change sign. And then we'll do this again, but this time using the right reflection. In this case, what we're going to see here is that this x value at -1 is going to reflect over here and become a +1. So here we are going to reflect over the y-axis. So if we put the negative on the y, then we reflect over x. If we put the negative on the x, then we reflect over y. So we see this a lot of things that act like opposites. This point here is at 0, 0. So my x component, 0 turns to -0 to 0. So this point stays. This point here that we have at -2, 0 is going to flip over here because this -2 on the x is now going to become a +2. Let me get rid of these points here. We'll just use a couple points because we don't have as many zeros. We're going to reflect like this. All right, so you have two of these to work on. So this is your fx, so you're going to do the reflection of f of -x. And then you're going to have the same cubic, but now you're going to do the reflection and you're going to do -fx. Don't be surprised if you see something that seems a little weird here. All right. Hopefully take a minute there. So we see that the negative is on the x, so x changes sign, which means x that is over here would over here. So we are going to reflect over y-axis. This point here at 1, 1 will now reflect over here to -1, 1. This point here at 0, 0 is going to stay at 0, 0 because there's no reflection from there. And then this point at -1, -1 will reflect over here and will now be at 1, -1. So it's just that x component. That's changed sign. Oops. Sorry, my board slid when I was doing that last bit there. Let me do that one more time. Sorry about that. We'll just pretend it went to that point. I keep missing it for some reason. There. Okay. You may have noticed Now with this one here, now we have the negative out front, so that means we have negative y's. The y changes sign. That means a y value, if it changes sign, would go from here to here. This means I'm going to reflect over x. So this point here at 1, 1 will reflect down here and would become 1, negative 1. And this point here at 0, 0 is 0, 0. And this point here at negative 1 reflects up here to a point where now it's at negative 1, 1. So we ended up getting the same function back. In this case, both of these reflections are the same. And the reason that works is because this is my definition of a odd function. If you have odd functions, either reflection, if you reflect over x, you reflect over y, will give you the same graph. So sometimes you'll see things like that. If you have an even function, all even functions, if you do a reflection over the y-axis, or so, yes, over the y-axis, you'll get the same graph back. Some fun things about reflection.